Okay, this is a requested video from one of my students on how to solve for the pH of a buffer solution using an ice table. Now, if you're not familiar with ice tables, I do have another video all about how to use an ice table and why we use ice tables. So if you're confused right now, go watch my ice table video and then come back to this one and you'll be a lot less confused on what I'm doing. So the whole purpose of using a buffer solution is to resist changes in pH. Typically our buffer solutions are composed of a weak acid, which in this particular example is HF, and its conjugate base, which in this example we're told NaF. So most of your general chemistry college professors, and maybe high school too, won't tell you the reason why this sodium ion is here. Basically, what happens when this is in solution, it's not present as the sodium fluoride you see here. It's actually present in its different ions, Na plus and F minus. We don't really care about the sodium parts. This, however, this is the conjugate base to the weak acid that we're using. So this is really what we're interested in. Whenever you get into your upper level chemistry courses, they'll refer to this as a counter ion, which all it's doing is stabilizing this F minus ion. But if you have any more questions about that, you can request a video or I'll tell you a reason why we use counter ions and all that. Okay, so we're presented this question. We want to find the pH of a buffer solution made from 0.3 molar HF and 0.7 molar NaF. And we're given a Ka value, 7.1 times 10 to the negative fourth. So I like to deal with any kind of math like this in chemistry first by making a chemical equation. So we know that usually we add our acids to water, to liquid water. And we also know that with an acid, all that happens is this hydrogen jumps onto the water and we have H3O plus. And then since that hydrogen left and went to the water, we're left with just F minus. And the H3O plus, that's what is controlling our pH. Okay, so let's set up our ice table. Now, when you're making an ice table for a buffer solution, some students get confused when you get down to the equilibrium part, because more or less everything is the same, except for now you know a concentration for a reactant and you know a concentration for a product. But that doesn't matter, and I'll show you why. So we're starting with a concentration of 0.3 molar here. Liquid water, we don't care about that at an equilibrium. We don't have any H3O plus yet. And now what's different from a traditional ice table is we know the concentration of this too, which is 0.70. So just like any other ice table for an equilibrium, we're going to lose an X amount here, we're going to gain an X amount here, and we're going to gain another X amount here. Just like any other ice table, we're going to sum up our I and C rows. So for this, ends up being 0.30 minus X. 0 plus X is just X. And 0.70 plus X. This part is different from a regular ice table, but don't let it trip you up. Again, just like any other ice table, we're going to set up our equilibrium expression, which if we're talking about a weak acid, it's Ka, and that's equal to the concentration of our reactant, or our products, over our reactants. So our products here are F minus and H3O plus, so H3O plus, F minus, and that's over our products. We don't care about water, we're just going to use the HF. Okay. we have all these values. We're given the Ka in our problem up here, so all we have to do is plug and play. That was our value given. All I need to do is plug in the amount for H3O, which is X. Our amount for F minus, which is 0.70 plus X, divided by our HF concentration, which is right above me here, 0.30 minus X. Now here we have to make an assumption, because if we try to solve for X, we get some pretty nasty math going on. So if our Ka is pretty small, I mean that's a pretty small number, that's 0.00071, I think that's a pretty small number. So in order to kind of ignore some of the rules of math, we are going to say, well, that X doesn't count and this X doesn't count either. So we're just going to continue on without those. Which that brings us to something that's a lot easier to solve. So I'm just going to multiply this times that, 0.70x. So my 7s tend to look like 2s sometimes. And on the bottom, since we got rid of that x, we just have 0.30, and all that is equal to the Ka value we were given in the problem. Okay, this looks a lot easier to solve, because now all I have to do is move this over here by multiplying it out, and I'm going to drop down here to do that. And this is 7.1, not 0.4. Okay, so 7.1, 10 to the negative 4th, times 0.3. 2.13 times 10 to the negative 4th. All we have left over on this side is 0.70 times x. We just divide that to get our x value. 3.04 times 10 to the negative 4th is what we get, times 10 to the negative 4th. And that is equal to x. Now, we need to make sure, we're looking for pH, so we need to make sure that this x is indeed at equilibrium, our H3O+. We refer back to our E row, and we see, okay, H3O at equilibrium does equal x, so we don't have to do any more calculations. So this actually equals the concentration of H3O+ at equilibrium. So to find the pH, I'm going to use an equation that you've probably seen before if you are at this level of chemistry. So our pH is just the negative log of our H3O concentration, which we just found right there. So pH equals negative log of 3.04 times 10 to the negative 4th. I am in the works of getting a new camera, I swear. Okay, so negative log of that answer that I just found, 3.52. 3.52. This should be our concentrate or our pH with the given concentrations. Just to kind of run a check on yourself. Whenever these two values combine, and this is another video I'll have to do, this is a property of a Henderson-Hasselbalch equation, which you will learn about in your chemistry course. Whenever this is operating perfectly, our pH is equal to our pKa. And all our pKa is the negative log of our Ka. pH in this circumstance should be approximately the negative log of 7.1 times 10 to the negative 4th. And this is just how I check myself whenever I'm doing equations like this, to the negative 4th. 3.15. So it should be about 3.15. We look at what we actually received. That looks pretty good. In pH terms, whenever we're operating at with a good buffer, we're given +1 or -1. So technically our operating range is about 2.15 to 4.15, which we're within that range right there. So this is a good way to kind of check yourself on buffer systems.